So on the other side, I can have multiple output and one encoder here for my data. And the representation that will be given by my encoder, maybe it's relevant for different tasks. Maybe this representation can be used to predict different things in parallel, because all the tasks share the same data as input. And this is called multitask learning. So here my task is, the first task is to say what is the object in the image, the color of the object in the image, and the last one is it dangerous or not? So 3 tasks about 3 different questions, but they are all about the same image as an input. So I will try to use only one encoder to have one representation here, and this representation will be given to 3 decoders that will predict the output. And by doing so, the representation must preserve all the features relevant for all the tasks together. So maybe the features of the color of the object will in some way help the first task to detect the object in the image. And by training simultaneously with the 3 tasks, maybe I will have better features that will work well for all my tasks. So if you are really interested in the first prediction, but you have information about 2 and 3 in your data set, you can use multitask learning to train your model to achieve 3 tasks in parallel, and you can look if it helps the first task to do so. There are also examples where 2 tasks can be a little bit contradictory. They can fight each other because they are very at the opposite. And so the features will be aligned only for 1 or for 2, and it can not work very well in this case. So multitask, you should use it if you think that predicting 3 properties of the same object will help you to predict what you want to achieve. Another pattern is the teacher-student architecture. And it's related to yesterday when I said at the first iteration, you should not take into account all the constraints from deployment and from engineering. Because here what we can do is we take our data in the task and we will explore all the possible architecture to find a good model that will generalize. And when we have a good model that generalizes, we will call it the teacher. And we will not use the labels anymore. And so we will create a new model called the student. The student will meet all the requirements that you can have from deployment and engineering. So very often it's a much more simpler model. And instead of training the student on the labels of your data set, you will try to mimic the output of the teacher model that you have trained before. And it can be super counterintuitive that the student model will perform better, will generalize better by predicting the output of the teacher instead of learning on the true labels. But it has been verified many times in the literature that it's the case. It's much easier to train a small model from the output of a complex model than from the true labels. Intuitively, a label doesn't have much information. It's only yes or no. Is there a cat, 0 or 1? The teacher will provide a probability. It will provide a number between 0 and 1. And it can be much more informative about what are the easy examples and what are the hard examples in your data set. And learning from the probability can be much easier for the student than learning from the true labels where the signal is less powerful. And it's really used to do model compression, so that after that you can use the student model to deploy it on a cell phone, as an example. So the modulation pattern, it's using a module to try to change the range of your representation. Deep learning, people had the idea of deep learning with the compositionally compositionality principle for many years, but only 10 years ago they were able to really train a deep neural network. And the difficulty of training deep neural networks was coming from a modulation problem, where the representation were going on several orders of magnitude from minus 100 to 100, and training with this range was super hard to do for deep neural network. So when people realized that it was because of the order of magnitude of the representation, they invented modules to try to modulate the amplitude of the representation. So in LSTM, as an example, you will see the gating mechanism. We'll use some sigmoid function to learn which information to keep and which information to forget, so that the representation will not vary over a big range. We can also have skip connections, where instead of all the representation going through all the sequence of modules, we can skip some modules from time to time, so that if I have a good signal from the beginning, this signal can propagate more easily in the architecture, just by skipping the modules. We can also use batch norm, which will do some statistics to normalize your representation. Film is a variant that is adaptative. It will do batch norm, but according to the data that you have as an input. It's an adaptative version of batch norm. And also you have attention mechanism that you will see on Thursday that are very powerful modulation techniques. And so the last pattern that we will see is the bottom-up approach. So here it's to use some intuition from the task and try to encode it in the architecture. So here the task is to answer to one question about this image. So is there one person doing skateboard on this image? Let's say it's the question. I will take this image, I will take this question, I will encode it, give it to the model. I will take this image, encode it, and give it to the model. And now the model must analyze this image and answer to this question. Is there someone doing skateboard in the image? So one way to do it is to maybe segment this image into tiny patch on a regular grid and give it to the model one patch after the other. And we hope that the model will combine all the information from these tiny patch to find the skateboard, the person, and to forget about all the information around the element of interest. And it was not working very well to do it in this way, because as a human, if you ask me a question about this image, I will look very quickly to the different elements that I think are relevant, and I will focus my attention really on the center of the image here. And then it will be easier for me to answer to the question. And to try to mimic a little bit my process to answer the question, I will use one detection module here that will provide me all the bounding bots of element of interest in the image. And with all these bounding bots, then I will give it to a predator, and it will be easier for the predator to find the information in order to answer the question. So because I knew that it's easier to look at certain part of interest, I will learn first what are part of interest in image in general. I will use it as a sub-module, and then the answer I will provide it to another module that will answer the question related to these concepts. So it's called the bottom-up approach. The top-bottom approach is really using a very huge model, end-to-end learning, where I try to learn from one image to answer the question. The bottom-up approach is there a way to simplify the work by decomposing my task into subtasks and having one module to achieve each of the subtasks? So the take-home message is, with deep learning, we can define hypothesis classes with computational graph easily with these modules, And this afternoon, you will create your first computational graph. Probably not your first. I heard that many of you have already done deep learning, but we'll build the first computational graph of this deep learning tool. Creating a graph for a given task and dataset is part of the expertise in deep learning. An architecture often have many layers, each providing a new distributed representation for the next one. And we try to the modules try to simplify the representation so that at the end, answering the question is very easy. And design patterns for architecture are emerging in the literature. It's not something that is well documented, I think, but we can clearly see these patterns. You will see the attention mechanism patterns in details on Thursday. And the attention is one of the most used technique now in natural language processing. So I think it's important to try to understand how to create the intuition and how to create new architecture given a task and a data set. Thank you very much.